Alright, so here's the general result. Suppose we have a length k chain of generalized eigenvectors. So suppose we have vk pointing to vk minus 1, pointing to all the way to pointing to v2, to v1, to 0. And this is associated to eigenvalue lambda. So all the arrows indicates multiplying by a minus lambda I. Zero. Okay. Gives you a solution. Has a corresponding solution. So we have C1 times e to the lambda t times V1, because V1 is the eigenvector, and from here the term starts piling up. So for V2 we have C2 times e to the lambda t times V2 plus TV1, and C3 is e to the lambda t V3 plus TV2 plus t squared over 2 v1. So to notice the pattern, the 2 is secretly 2 factorial. So now we see the pattern. So the last term is ck times e to the lambda t vk plus t vk minus 1 plus t squared over 2 factorial times vk minus 2 plus all the way to t to the k minus 1 over k minus 1 factorial times v1. So this is what happens when you have a really long chain. In reality, our chain is not going to be longer than 3, but this is what a corresponding solution looks like if you have a really long chain of generalized eigenvectors. Alright, so let's do an example, not regarding this, but let's do a 4x4 example. So let's consider x prime is 1, 3, 7, 0, 0, negative 1, negative 4, 0, 0, 1, 3, 0, 0, negative 6, negative 14, 1, x. So this is a matrix A. So first we solve the characteristic equation, which is determinant of A minus lambda I equal to 0. So 1 minus lambda, 3, 7, 0, 0, negative 1, negative 4, 0, 0, 1, 3, 0, 0, negative 6, negative 14. I forgot a minus lambdas here. 1 minus lambda equal to 0. First column is mostly 0, so let's do the first column. So this is 1 minus lambda times the smaller determinant (14). 1 minus lambda equal to 0, and let's do the same thing for the third column because it's mostly 0. And this is plus minus plus minus plus. So this is plus. So we have 1 minus lambda times another 1 minus lambda times this 1, 3 minus lambda, right. Negative 1 minus lambda, negative 4, 1, 3 minus lambda equal to 0. This small part is equal to lambda, negative 1 minus lambda, negative 1 minus lambda times 3 minus lambda, minus negative 4 times 1. So that's lambda squared plus 2 lambda, minus 2 lambda. Lambda squared minus 2 lambda, minus 3 plus 4, so plus 1. So this is lambda minus 1 squared. So all the factors are the same, pretty much. So the eigenvalue is lambda equal to 1, and multiplicity is 4. So there's only a one eigenvalue, so let's try to solve for eigenvectors. So let's first solve a minus I times v equal to 0. A minus I is 0, 3, 7, 0, 0, negative 2, negative 4, 0, 0, 1, 2, 0, 0, negative 6, negative 14, 0, times v equal to 0. Okay, so the second and the third row are dependent. The second row is the third row times minus 2, so this doesn't tell you anything. The fourth row is the first row multiplied by negative 2, doesn't tell you anything. If you look at these four parts, this tells you 3v2 plus 7v3 equal to 0, and v2 plus 2v3 equal to 0. And because the determinant 3, 7, 1, 2, this is negative 1, which is not 0. So this directly tells you that v1, v2, and v3 are both 0. And so the free variables are v1 and v4 are free variables. So the solution is, so if v1 is a free variable, then it's 1, 0, 0, 0. And if v4 is a free variable, then it's 0, 0, 0, 1. So these are the two solutions. So the diagram for generalized eigenvectors looks like 1, 0, 0, 0 pointing to 0 vector, a minus I, and 0, 0, 0, 1, a minus I, pointing to the 0 vector. So because there's only two eigenvectors, lambda equal to 1 is defective. And then defect is 4 minus 2, which is 2. The problem with this is, so now we know there's going to be two chains of generalized eigenvectors, but we don't know how long they're going to be. It could be length 2 and length 2. It could be length 3 and length 1. So we don't know which case it's going to be. But the process is similar. So to find a longer chain of generalized eigenvectors, all we're going to do is we're going to make a guess. So let's start with the vector 0, 1, 0, 0. We didn't guess 1, 0, 0, 0 because it already appears here. We don't want to guess the same thing. So 0, 1, 0, 0 is the second easiest thing to guess. So if we start with 0, 1, 0, 0, then we try to multiply this by a minus I. Then we get 0, 3, 7, 0, 0, negative 2, negative 4, 0, 0, 1, 2, 0, 0, negative 6, negative 14, 0, multiplied by negative 1, 0, 0. This is equal to 3, 2, 3, negative 2, 3, negative 2, 1, negative 6. And then let's multiply this by a minus I again. So we get 0, 3, 7, 0, 0, negative 2, negative 4, 0, 0, 1, 2, 0, 0, negative 16, 6, 0, negative 6, negative 14, 0, times 3, negative 2, 1, negative 6. This is equal to 1, 0, 0, negative 2. Okay, I'm going to move stuff around. And matrix still visible. And let's multiply by a minus I again. 0, 3, 7, 0, 0, negative 2, negative 4, 0, 0, 1, 2, 0, 0, negative 6, negative 14, 0, times 1, 0, 0, 2, negative 2. This is going to be all zeros, which is a 0 vector. So this is the length 3 chain of generalized eigenvectors. So this is our v1, v1 is here, and v2 is here, and v3 is here. So we have our v1, v2, and v3. We have a length 3 chain of generalized eigenvectors. So we need v4, which is a length 1 chain of eigenvector. And same thing, either one can be v4, as long as it's linearly independent to v1. And v1 is 1, 0, 0, negative 2. That is parallel to neither of them. So let's choose the top one to be v4. Okay. So there you go. We get A is equal to P times J times P inverse. P is the matrix with v1, v2, v3, v4 being the columns. So it's 1, 0, 0, negative 2, 3, negative 2, 1, negative 6, 0, 1, 0, 0. That's v1, v2, and v3. And v4 is 1, 0, 0, 0. And J is the Jordan block. The diagonal is the eigenvalue, so it's 1. So because we have a chain from v3 to v2 to v1, so this is a block, and v4 itself is a block. So everything outside is 0. Everything below the diagonal is 0. And because v3 is pointing to v2, so this is 1. And because v2 is pointing to v1, so this is 1. And this is 0. So this is the Jordan block for Jordan form for A. And the general solutions is x equals to, it's going to be 4 things. v1 is an eigenvector, so it's c1 times e to the lambda t. Lambda is 1, so e to the t times v1 plus c2. v2 is pointing to v1, so it's e to the t times v2 plus t v1. And v3 is pointing to v2, pointing to v1, so it's v3 plus t v2 plus t squared over 2 v1. And v4 is by itself, so it's c4 times e to the t times v4. So this is the general solution. If you want to write it in scalar form, we first expand the vectors, so c1 e to the t. v1 is 1, 0, 0, negative 2 plus c2 e to the t. v2 is 3, negative 2, 1, negative 6 plus t times v1, 1, 0, 0, negative 2. And c3 e to the t. v3 is 0, 1, 0, 0 plus t times v2, 3, negative 2, 1, 1, negative 6, oops, 1, negative 6, plus t squared over 2 times v1, which is 1, 0, 0, negative 2. And c4 e to the t, v4 is 0, 0, 0. v4 is 1, 0, 0, 0. Okay. If we have that, then the general solution in scalar form you copy down the entries. So x1 is c1 e to the t plus c2 e to the t, 3t plus 3 plus t, and plus c3 e to the t, 3t plus t squared over 2 plus c4 e to the t. And x2 is, there's no c1, and c2 e to the t, negative 2, that's it, plus c3 e to the t, 1 minus 2t, there's no c4. x3 is no c1, c2 e to the t times 1, c3 e to the t, 3t, and x4 is negative 2c1 e to the t plus c2 e to the t, negative 6 minus 2t, plus c3 e to the t, negative 6t plus minus t squared, no c4. Alright, so this is how you solve a larger matrix with higher multiplicity.